So my lagniappe has to do with stability, and that's what I'm going to start talking about now. Since it's used in many fields, I think I should mention a couple of applications of stability. The people that probably have the strictest definition of stability are people who deal with partial differential equations. And the usual way you see people do this is they will find what's called an equilibrium point. It's some place where you have a solution to the equations where the parameters are constant. Then you disturb that configuration and you calculate what happens to the solution in that case. If the solution never goes far away from the equilibrium solution, then it's called Lyapunov stable. If it comes back to the equilibrium position, like a damped system that you just tapped, then that's called asymptotic Lyapunov stability. And if the solution takes off for infinity, then it's unstable. So you will find people that devote a lot of time looking at stability. Solomon Lifshitz at Brown was one such person. There's another way of looking at stability, and if you look at classical thermodynamics, the concept of stability is present. And usually the way it's explained there is to say, I'm going to have an isolated system. And if you remember your first law, there's another one of these clouds, and there's an arrow pointing out for work, there's an arrow pointing in for heat, and an isolated system is one where both of those quantities are zero. So the thing usually written as W and the thing usually written as Q are both zero. The only thing that's left is E on the inside, which is somehow the energy of everything that's in this cloud. Now, the way the classical thermodynamics, and more or less the Gibbsian version of thermodynamics, goes at this is they say, okay, I've got something in a jar here, and it's having a spontaneous reaction. Okay, that could be a chemical reaction, anything. And I want to consider what goes on there. And by using the Clausius-Duhem inequality, or what some of these books call the inequality of Clausius, that's right. By using that, you can show that if there's a change, then the entropy has to increase. Therefore, anything that's happening in this cloud where there's no work going in or heat going out, whatever's going on in there is increasing the entropy. So the equilibrium state would be when you reach the maximum for the entropy. And otherwise, you would say that the state is at least temporarily unstable, but maybe it's going to a stable state. Let's hope it is, but it's a maximum entropy condition, and that's a very reasonable sort of a definition. Now, people study materials from a thermodynamic point of view, and a good friend of mine, Mort Gerten, has spent a lot of time doing this sort of thing. And Mort's a rather accomplished fellow. he went to, well, let's see, we started out together at General Electric Company as engineers, solving large eigenvalue problems, or at least large in those days. And I guess we both wore out, because in 1959, both of us left GE, and Mort went to Brown, where he picked up his PhD, became a member of the faculty of the Division of Applied Mathematics. That lasted till about 1966, when he went to Carnegie Mellon, where they had still have, a very strong group in continuum mechanics, and they look at these sort of thermodynamics of materials kind of problems. I think the two best known people there are Bernie Coleman and Walter Knoll. And Mort worked with them for a number of years. And recently he won the Timoshenko Medal, and that's good. So he's written a book. I got a file copy. I don't know if it's been published yet. I don't even know who the publisher is going to be, but I do know the name of the book. It's The Mechanics and Thermodynamics of Continua, with the Latin spelling. And it's written by Morton E. Gurtin, Gurtin, Elliot Fried, and Lalit Anand. And one of these days it'll come out, but it looks into these sort of things. And here's the sort of the trick. You write down your constitutive equations, and in plasticity we've been through all that. Then when you look at this this energy E, how do you know what the entropy is? And the truth is that for E, you need to split it up, because I think you can make a very good case that there must be an entropy function. Life just won't go on without an entropy function. So you have to split this E into what's called a dissipative part and a non-dissipative part. The part that's non-dissipative, you hook on to the definition for the entropy, and the other part you just leave alone. It's going to eventually go away in the form of heat, or it's going to raise the temperature of the isolated system. Something like that's going to happen. So if you do that, then you have a definition for entropy for your material, and you can tell then, or you can determine when it's going to head for a maximum and when it gets there. So that's a different definition of stability. The one I want to really talk more in detail about is the one that mechanical and civil engineers know most about, and it may be the only one they've seen, who knows. And this is for mechanical systems. There's several ways to go about solving mechanical systems, and there's a method in my madness. I want to go through those, and then I want to talk about those in terms of the Drucker stability postulate. So that's what I'm up to. In this first slide concerning this lanyard, I've got a picture that contains some sketches for 4 problems. And think of this as a matrix. There's 4 pictures on the top, there's 4 pictures on the bottom, and then there's 4 columns. And I'm going to do these problems in order. And these look real simple. They are real simple. I want them to be simple, because I want to talk about what's in there, not the solution to some particular problem. If I look at the upper left figure, I've got a rigid bar, and it's connected to rigid base, if you like, and it's held there by a torsional spring. This rigid member doesn't have any weight. I'm trying to make it as simple as I can. So all I've done is I've dumped a load on the top. The length of the bar is L, and the torsional spring constant that holds the bar vertically when there's no load on it, that torsional spring constant is K. So that would be inch-pounds per radian, something like that. And in this, when I load that, then what I'm going to look at is I have to go down to the second row, first figure. Okay, and all this thing can do is tilt over through an amount alpha. It's a 1 degree of freedom system, and you can see the load sitting there on the top moving over. And because the load does that, it has a potential energy. Well, what does that mean? It means that no matter how I get from one place to the other, the work is the same from the load. Now, the second column, the picture in the first row looks the same, in fact, is the same as the one we just talked about. But now, when I allow the bar to move over, the load stays with it. And that's called a follower load. That's got some interesting characteristics. In general, you would not have a potential energy, but this case is so reduced that you can't even say much about it. Okay. I'm doing those just to get everything warmed up. The third problem is two links. Each bar has the same length, each torsional spring has the same stiffness, and it sticks straight up if the load P is 0. And now I put the load that has a potential energy on it, and I get 2 degrees of freedom, alpha and beta being the coordinates I'm going to use. And then this analogous thing for the last problem, except that it has a follower load. So we want to take a look at those, or at least I do. And the first two problems can't wiggle like a column, so it's not too surprising that their solutions differ a little bit from the last two, which can form a kink and do all sorts of things. A little bit more interesting to look at. I'm going to restrict all this to small displacements. I'm going to do everything I can to make this simple. So whatever it takes, that's what we'll do. In the next slide, I start on the first problem. That's 1 degree of freedom with a potential energy. And I've got a picture of the tilted version from the previous slide. And all I do is take the moment about the base, and I see, what's going on here. So when I take my moments, the alpha cancels out, and I get P is K over L. So I get a solution when P is equal to K over L, and it goes over. If you have a physical imagination about these kind of things, you would realize that if P exceeds K over L, this thing is just going to keep flopping over. And in an equilibrium method, you sometimes have to use that kind of imagination to determine exactly what's going to happen. When I use the energy method to solve this problem, then I have to write down the potential energy. And in this case, I don't want to drag everybody through all the details, but this first one, let me just mention that for a spring, the potential energy is 1/2 K times the displacement squared. And that's what I've got here. and then the potential energy includes the work, and the work in this case is how much the load P moves downward. And so I have a 1 minus cosine of alpha, and I'm using small displacements, so I get alpha squared over 2 for that. And the potential energy then looks real simple. I do what you always do in an energy method. I take the variation of the potential energy. In this case, it's just the derivative with respect to alpha. That always gives me the equivalent of equilibrium equations. Sometimes when you use this energy method, you're taking a little bit different viewpoint. That is, if I had a system that had an infinite number of degrees of freedom, and I guess a solution, and I calculate the potential energy for that solution, it's only going to contain a finite number of shapes, because that's the way I chose it. I took first 3 terms of a sine series, something like that. So then when I take this so-called first variation, all you do is wiggle the coefficients and take the linear terms. And the terms are independent, so I end up with equations, but they're not really general for the problem, but with the hopeful thought that if I've made a pretty good guess, that these equations that result are the best shot I've got at writing the equilibrium equations with this delimited displacement shape. So in this case, this is nailed because we know what we have. So alpha has got to be 0 for the equilibrium configuration. But we have to look a little farther. In an energy method, we have to take the so-called second variation, which is just the quadratic terms in these displacements. The way most books do this, and the way I like to think of it, is you've got a sphere in the bottom of a valley. It's at the dead bottom. So if you push it to the side, it rolls back. Okay. Then in that case, the second variation of the potential energy is greater than 0. If I take the ball and put it on top of a hill and move it over, it rolls down the hill. Okay. And in that case, the potential energy is decreasing, and it's unstable. So stability is dependent on having the second variation of the potential energy be greater than 0. And in this case, the load has to be less than K over L. So if you're used to working these problems, the solution to the first problem is the same as the solution to the second problem, unless you're just very fastidious. In the dynamic problem, you do something a little different, and we're going to have to use this dynamic method on a little bit later. And what you do is you take the problem you had and you throw some mass in somewhere. And what we've got here is I've put a moment of inertia, I-O, at about the lower end of the bar. So when I write the equation, I get the same thing I had in the equilibrium model, but I've got a dynamic term on there. I've got I times the second derivative with respect to time of alpha. So that leads me to a classical differential equation. It's I-O alpha double dot times K minus PL times alpha equals 0. You know how to solve that. You know how to solve that problem. What you do is you take alpha is e to the something t, and I've anticipated here and I've made it e to the I omega t, so that I get cosines and sines if omega is real. Stick this into the equation and solve for omega, and you get something that this is omega squared. So if this number is positive, okay, I get a real number for omega. I don't care if it's positive. I get a real number for omega, and then my solution is just a bunch of sines and cosines, and so it'll keep on vibrating forever, but it doesn't go far. So this would be something like Lyapunov stability, but not asymptotic stability. On the other hand, once P gets big enough to make this thing negative, then my omegas are imaginary numbers, and the e to the I omega becomes a real number, and it goes to infinity, so it's unstable. So all three of these give answers that to me look the same. Let's look at the second case, 1 degree of freedom, but a non-conservative load. The equilibrium method is sort of trivial because the bar tilts over, the load tilts over, the bar stays in compression, and nothing happens. It doesn't buckle. So the answer is it doesn't buckle. In the case of the energy method, the only energy, you see, you're really strictly speaking now, I should say, there is no potential energy for a follower load. But this is a very degenerate case, and you can pretend there is a potential energy, but that's because that P does no work, and it's zero, so what do you care if it's dependent on a point? It doesn't matter. So in that case, you can take the variation, you come up with alpha equals 0, you take the second variation, and you get this quantity k, which we've always pretended is positive, and the change in the angle is squared, so it's always positive and it's stable. Using the dynamic method, same as before, I mean, all I'm doing really is losing the contribution from P in this problem. And I come out with the differential equation, and P, this time I said alpha is something times e to the pt. P squared turns out to be negative. I get imaginary numbers, plus or minus an imaginary number, and I get sine waves. So that's the 1 degree of freedom. Now it gets a little more complicated, but not horribly, I think. We get to even use a little bit of linear algebra, which just keeps coming up in this stuff. Well, first case is the 2 degree of freedom system case with potential energy, meaning that the load doesn't rotate. And I don't think we need to drag ourselves through all of this, but when I write the equilibrium equations for small alpha and beta, I get the first two equations on that slide. And if you look carefully at those, can be written in matrix form as a matrix times the vector alpha beta, column vector alpha beta. And if I have a square matrix times a column matrix, and the right-hand side is a column matrix with all zeros, I have to have the determinant vanish in order to have a non-trivial solution. So we want to take a look at that. The determinant of this matrix has to be 0 now. So that's indicated in the third and fourth lines on this page. And all I'm doing is taking, that is the coefficient matrix for the equations above, and I'm setting the determinant of that equal to 0. When I do that, you can see that I'm going to get a quadratic equation in PL over K, which I've written there. And we get two roots, of course, because it's that way. And I give the two roots, no, I don't give the two roots. I give the lower root only. And why would you do that? And because you get there first. Because all the stability stuff is based on starting with a low enough load so that you're not buckled, and you increase the load until you get a non-trivial solution. And that's what happens in design. You design something and you assume that the load goes on gradually, and you hope it never gets to the buckle load if you've tried to design some kind of a structure. Anyway, we get a result here for the load that's 3 minus the square root of 5, all that divided by 2. And for the shape, we get 1.618. What does that mean? The shape means that when we buckle at that load, the relationship of alpha to beta is, as indicated, is the 1.618, and that would correspond to the buckled shape. And that's the way something like this works. It's essentially an eigenvalue problem, with the load being the eigenvalue, and the beta and alpha then are the corresponding mode shapes. If I use an energy method on this, then I've written out what the energy of the springs. Remember, they both have the same torsional spring constant, and this is just straightforward geometry. I take the variation, which means I can be a little more explicit here. I let alpha go to alpha plus delta alpha, and I let beta go to beta plus delta beta. Stick that in the potential energy, cull out the linear terms, and that's the first variation. That's the way you do it. And when I pull out the quadratic terms, then I get the second variation. Okay. The first variation should give me the equilibrium equations. Now, when I do what I just said and take the linear terms, when you take these variations, alpha and beta are independent. And that means, in this case, physically, I can vary alpha and keep beta constant, and I can vary beta and keep alpha constant. So that means that if the variation of the potential energy is to be 0, which it must be, because that's one of the big theorems in mechanics, then the coefficient of delta alpha and delta beta must separately vanish. When I do that, I get the equilibrium equations from up above. But the more exciting result is to get the second variation. And what you see here is I've got the second variation of the potential energy. It's in what a linear algebra book would call quadratic form. It is a quadratic form. And if that's the case, what I want is I want that quadratic form to be positive definite. And what do you do in something like this? Well, you look at your linear algebra book. It's probably the easiest thing to do. But all these linear algebra type books show that each of your discriminants must be greater than 0 in order that this expression be positive definite. So what's a discriminant? In case you don't remember, I'll tell you. You go down the square matrix, you start with the 1 by 1 element, that's a little matrix, and you calculate its determinant. Then you step down, you do the 2 by 2 in the upper left-hand corner, and you calculate the determinant. and that's the second discriminant. And in this case, that's all there is. So you write down your two discriminants, and they must both be greater than 0, or you don't have a stable system. So it turns out that the controlling answer here is, here I do give the quadratic form. I get this PL over K as, each discriminant is going to give me different values for P. So I take the minimum, and I get that PL over K is this 3 minus square root of 5 divided by 2, which is precisely the answer I got in the equilibrium method. If I do the dynamic method, I need to go to the next slide. And the situation is somewhat similar here. But you end up having to put in some masses if you're going to do the dynamic case. So I just stuck a mass at the upper end of each bar, and I've written the equations, and there's a little bit of algebra that you play around with, but you get a pair of differential equations. That looks like that's about the 4th and 5th equations on that slide, and you do what you do with these linear constant coefficient differential equations. You say alpha is a e to the I omega t and beta is b e to the I omega t. Stuff that into the equations, and you get solutions for a and b given from a homogeneous set of equations. And the equations are there, zeros on the right side. So the only hope is that the determinant vanish. And I struggle through all of that, and lo and behold, I get the same answer I got the last two cases. So as you can imagine, this isn't very exciting, but this next one makes things a little more exciting. And that is when we go to 2 degrees of freedom with a follower load. When you try to write the equilibrium equations, there's no alternative but to have alpha equal beta. And then alpha has to equal 0. So there is no solution according to this. But that's not true, you see. That's why we're doing all this stuff. And if you think about an energy method, I've got a little thing here. What I'm trying to show is that the work done by the load is not path independent. And it's easy to do that. You let alpha be something while beta is 0, calculate the work done by P, and then do it the other. Well, you have to let alpha be something and then beta be something, but then you switch it so that you have a different scheme. You put the alpha first and the beta second, or beta first and the alpha second. And what you find is the work done by P is different in both cases. So in the case of the energy method, you just have to throw up your hands. It doesn't work. So forget about that. In the dynamic method, you can write your equations and go through pretty much the same thing as we went through in the earlier problem. And I end up then with this dynamic method with this pair of equations, and the equations are given there as, with the a and b equal to 0. One thing that a person who's been around this stuff for a while might look at that and wonder why that coefficient matrix isn't symmetric. But it isn't. It's what it is. So you can solve that using the usual stuff, the usual solution for differential equations. And you come out with a number of, for the load, in order to, the load has to be less than this value in order to avoid the determinant being 0. And it's less than 2k over L. So the equilibrium method really didn't resolve anything. The energy method is not valid, you know, and the dynamic method works okay. Well, if we go back and look at what we had for the load when we used the load with the potential energy, let's see now. I got, for that PL over K, I got 3 minus the square root of 5 over 2. Okay, now square root of 5, what do you suppose that is? 2 something. 2 point something. Okay, I take 3 minus 2 point something. I've got less than 1. I divide by 2. I've got a number less than a half. Okay? And over here, my number is less than 2. So this load is 4 times higher. It will buckle, but at a much higher load. Well, if that's not enough to, you know, get you excited and so on, if you were to look at Timoshenko's books, he wrote about 20 books, and the one that you want to look at is the Theory of Elastic Stability. And in there, he takes a beam column, but it's a real beam. It can bend all over the place, so it has an infinite degrees of freedoms and all that. And he struggles away and solves that. And he writes his solution in terms of the corresponding solution for the load that's not a follower load, for the one that has the potential energy. And if you recall the Euler buckling load, pi squared EI over L squared, you know, everybody just ought to be able to be shaken out of their sleep and tell you that equation. So if it were not a follower load but a vertical load, the load you would get is pi squared EI over L squared. If you put on the follower load and struggle, as Timoshenko shows you how to struggle in his book, he gets a number that's 2.03 larger than the vertical load. So the follower load also, in this case, is larger. It's larger by a factor of 2. In our problem, it was larger by about a factor of 4. So that's an indication that when you're running around doing stability studies, it helps if you know a little bit about what you're doing, because these issues come into the game. Well, now I want you just to go back in your heads and say, now suppose I looked at this differently. Suppose in each of these problems I had the load on, and let's just look at the equilibrium method. If I were to, on that first problem, for example, if I were just to put a little side load up at the top where the load is and see how far it moves over. So get the picture. It's got the load on, the load is constant, it's just sitting there, and we're going to assume that for this first little bit of talking that it's below its buckling load, so it's just sitting there with this load on it. Then I come up to the top and I push a little bit sideways, and then I let go. And does it come back or not? And if it comes back, that's another way of looking at stability, and it's a way that many books do. So I can do that with all of these problems, and in every case I can say that a small lateral load can be used to test stability. And in those cases, it's only going to come back if the spring constant is positive. That means that the load goes up when I push on it. Okay? That's the key. Taking that understanding, and now we return on the next slide to the Drucker postulate. It's the same slide you've seen before, but I just want to point out something different on this. This part where it says stability in the small, and we've got a d sigma times the d epsilon p. That would imply that my added load when I get to the yield surface does positive work on the plastic strain. That's virtually the same stability requirement that you have for these other problems where you put a little side load and see if the K is positive. Because if you have an unstable material, that won't be positive. And an example of this is a compacted soil. If I push on it, and it shears, it gets weaker. So d sigma decreases rather than increases. And you can say then that for a compacted soil, it's an unstable material. And I think that's a good way to look at Drucker's stability. That is, all these things, in a way, are the same thing. And not every write-up I've seen on stability is as charitable as I am concerning the compatibility of all these different schemes. That's all I want to say about stability. I want to make some closing remarks now concerning the whole course. And I guess these would be the things that I like to think I carry away from all this stuff. First off, that in spite of all these beautiful things like slip line theory and matters of that sort, the truth is that real plasticity problems these days are solved with abacus. The important thing is, with the stuff we went through, is that I think you can develop a feeling. So when somebody runs in with an abacus solution, you can look at it and say, this is impossible, and have some reason for feeling that way. A second item that I've brought up a couple of times, but I want to just say it again with maybe a little more detail. When we take something like a steel, and we're going to do something about plasticity with it, the Young's modulus, the shear modulus, Poisson's ratio, they're pretty nearly constant. You for steel, not too many arguments. I remember as an undergraduate, there was always a big discussion back and forth between civil engineers and mechanical engineers, usually in the local pub, concerning whether Young's modulus should be 30, which was the mechanical engineer's number, 30 times 10 to the 6 psi, or whether it should be 29, and that was more or less the civil engineering standard number. Well, that tells me, we're not really talking about much to be concerned about. But when you drift into plasticity, there's more variation in these numbers that we're getting, the yield point and all that. And a few years ago, there was a joint industry project done by virtually all of the majors, and they ran more stress strain curves than you can count and tabulated them and did a really nice job. If you ever get in a big company and you can get your hands on this joint industry project, you might enjoy looking at the numbers. the name of it is, of this report for that project, is DEA 130. And what I did is I went through it, and for each material that they tested, these would be, say, a material like L80 from several different suppliers. And I took the numbers and got the standard deviations and so on. And you're talking 5%. And these are samples sent by the steel companies to the project, so you know that's their best stuff. And the tests were carefully performed. But you see, there's a lot that sneaks in here. When you go to a steel mill and watch them make things, they may run off a heat which they expect to be L80. And it's got all the chemistry, and they run around and measure a lot of stuff. And they make the ingots and so on, and they test them. Well, what if it doesn't make it? It misses somehow, the chemistry, the guy didn't throw in enough carbon, who knows what. If that happens, that material is usually downgraded maybe to an L60, something like that. And so when you buy an L60, all they're telling you is that you're going to meet the minimum specs. And if you're lucky enough to get the almost L80 instead of the regular L60, you're going to have different properties. So you get a lot of scatter that way. Well, when you're ordering tubulars for an oil well, you don't know what you're going to get, and you've got to design the well before you can order the tubulars. So sometimes you wait 6 months to get the tubulars because they aren't really on hand. So there's no point in killing yourself getting an answer within 1% in plasticity. And I think that you can't say that enough times, because it's a very important engineering concept. Something I mentioned was the work by Don Wood trying to get upper and lower bounds on a three-dimensional limit analysis problem. There are many materials where you can show that the upper and lower bounds work, but the danger there, and it's not big danger, but it's something you have to be aware of, is that if you go to apply this to a soil or rocks, you want to make sure that you're meeting Drucker's stability criterion, or you want to develop a theory that will accommodate the unstable material. The next point I would make, something we didn't talk about, but I think I can show you what the concern is with just a few words. We didn't really work any elastic plastic buckling problems. And let's just think of the simple column sticking up, put the load on, make it a conservative, I don't care. And now the beam bends, it's going to buckle. And how do I analyze that problem? Well, there's really two ways of looking at these column problems, and they're in Timoshenko's elementary strength of materials books. And the one way is to start straight and then find out when you're going to go sideways. The other is to start with a crooked column. And in fact, the crookedness, that is the out of straightness of the column, appears in some design codes for structures. So people even know kind of what the limits would be. Well, if you analyze the problem starting with a crooked beam, elastically, there's very little difference between the straight and the slightly crooked. But in plasticity, what happens is with the slightly crooked one, it starts to bow out, and the the stress field is different from where you push it until it's fully yielded and then let it go sideways. Okay? Now, it doesn't take much imagination to figure out that you want to start with a crooked beam when you analyze buckling load. And a fellow named Shanley did a lot of work on that, but I seem to have lost my reference to his papers. So that's okay. The next point I would make, I mentioned this fellow whose name I still don't know how to pronounce, Morose, M-R-O-Z, something, it's kind of a mark over it. You know, he got into this sort of thing that was in Prager's book with these kinematic yield surfaces. And in his work, he got a whole bunch of these circles together, more or less like Prager does, but he works in a stress space rather than a strain space. And there's a subtle difference in doing that. And I believe that what Prager did is correct, and I'm not so enthusiastic about what Ross did. And the reason for this is that when I have a material, and maybe because of it's a polycrystalline material and it's got slightly different orientation of all the grains, that I think you're pretty close to having a uniform strain in the body rather than a uniform stress, because of the slip planes acting in the grains. And for that reason, I can't get as enthusiastic about the Morose model as I can about what Prager has done. And I think that wraps it up for plasticity. I have a couple of comments about fracture mechanics. And one has to do with this measurement of this capital gamma. In the oil industry, with these ductile materials, it is very difficult to get reliable results. I've seen results coming back from labs with quite a bit of scatter, and with a number of the samples not meeting the criteria that the standard says it has to. And in a way, it's a good thing to do, to use the fracture mechanics on these problems when you can get away with it. But it can be time-consuming and expensive. And the driving conclusion is that that the theory's just not as good for ductile material as it is for brittle. And there's people furiously working away, grad students all over the world trying to do something about it. And that's a good thing, and things have gradually improved. But from my own observations in the past couple of years, I think we should be careful in diving in too much. In fact, when I talk about the use of fracture mechanics in a ductile material and try to explain it, it's a little hard to keep a straight face. And I could imagine that it would be like an agnostic trying to give a sermon to a Baptist congregation, in that if you aren't really sold on something, it's a lot harder to explain it. So I'll leave you with that thought. I've had a lot of help with these lectures, and I'd like to just mention the people involved. And I'll probably mispronounce everyone's name, and one I won't even try. But Martin Cullen was, I guess, the big brains on the getting the equipment and arranging all things for these filmings. Brandon Mayahung, and I know I mispronounced that one, but he's been the person who's done most of the work, and I'm sure that in the cleaning up of the mess that I've made here, that he will be the one responsible for doing that. One of the fellows at Blade is Yubi Sathavali, who's been extremely helpful in helping me organize this. And then the name that I won't even try to pronounce, but he's the big man at Blade, so I definitely want to mention him. But his appellation is to everyone Suri, so that's about all I'm going to say. I've really enjoyed giving these lectures. It's been, for me, a lot of fun, and I hope it's been of some value to you.